So we have we have a function known as in underscore IRQ. So this function will tell us whether we are running in a hard IRQ context or not. So this, let's see what happens when I call this function from both soft IRQ handler as well as from the interrupt handler. So it will tell whether it is running in hard IRQ context or not. So interrupt handler, it is running in hard IRQ context, and soft IRQ it is not running in hard IRQ context. You can see IRQ handler is only running in hard IRQ context. Soft IRQ is not running in hard IRQ context. So the important points till now what we have seen which are related to soft IRQs are compile time. So we can only declare it at compile time and we have to add an entry in the enum. So it is not suitable for Linux kernel modules. Execution. So execution, it is executed as early as possible. So we after the return of a top handler and before the return to a system call. And how is this achieved? This is achieved by giving high priority to the executed soft IRQ handlers. Soft IRQs can run in parallel. Each processor has its own soft IRQ bitmap. And one soft IRQ cannot be scheduled twice on the same processor, but one soft IRQ can run on multiple processors at the same time. Priority, the kernel iterates, the do underscore soft IRQ method, it iterates over the soft IRQ bitmap, least significant bit first, and then execute the associated soft IRQ handlers. Case soft IRQD. Soft IRQs are executed as long as the processor local soft IRQ bitmap is set. Since soft IRQs are bottom halves, they can be interruptible during execution. So the problem here is the system can find itself in a state where it is doing nothing but serving interrupts and soft IRQs. Because soft IRQs are having higher priority, they will be served first. So system will be always in a state where there will be an interrupt, and then interrupt will raise a soft IRQ, it will execute soft IRQ, and then there will be an interrupt, soft IRQ. So it is doing nothing but serving the interrupts and soft IRQs. So incoming interrupts may schedule soft IRQs, which leads to another iteration over the bitmap. So such processor time manipulation by soft IRQ is acceptable under high workload, like if you are having high IO or network traffic. But this is not generally desirable for a longer period of time since user processes cannot be executed. Because you are always, the CPU is always handling the interrupts, soft IRQ and hard IRQ, user processes cannot be executed. So this is not a good behavior and should not be desirable for a longer period of time. So solution to the above problem is provided by kernel. So what kernel does is, after the 10th iteration, so this thing is there, max soft IRQ restart. If you look into the kernel, this will be set to 10. So we can also look here, cscope-d. It is set to 10. max soft IRQ. In the function they use in underscore underscore do soft IRQ, what they does is they use this max underscore soft IRQ restart. So what happens is after the 10th iteration over the soft IRQ bitmap, the kernel, what it does is it schedules a soft IRQ kernel thread, which takes the control over the execution of soft IRQs. Each and every processor, it has a kernel thread called as case with the name case of IRQD-n, where n is the number of processor. So you can also search here for case of IRQ. You can see we have in the Raspberry Pi we have 4 cores, so there are 4 threads for each and every processor. Case of IRQD-0 is for CPU 0, CPU 1, CPU 2, and CPU 3. So once the 10th iteration happens, the kernel will schedule this soft IRQ kernel thread, which will take control over the execution of soft IRQs. So then this particular kernel thread will execute soft IRQs as long as any bit in the soft IRQ bitmap is set. This way, the processor monopolization is avoided by deferring soft IRQ execution into process context, which is the kernel thread, and this particular soft IRQD can be preempted by any other user process. Who starts this kernel thread? So this started early. This function spawn k underscore k soft IRQD, which starts per CPU thread, and this function will call run underscore k soft IRQD. All the kernel threads will call this particular function when they are started, and they just internally call underscore underscore do soft IRQ. So you can see here in this file, this is the logic of underscore underscore do soft IRQ. So it is decrementing the value of max restart. And if this value becomes 0, then it is calling wake up underscore soft IRQD. This does not, it just wake up the process k soft IRQD of the particular CPU. So in this example, what I'm doing is I'm trying to raise the soft IRQ from the soft IRQ handler again, like up to 10 times. See what happens whether we get k soft IRQD as the name of the process. And you can see now, after some time, you're getting k soft IRQD. This is the kernel thread, which is actually executing the soft IRQs. After executing sometimes, this is the interrupted process. Finally, kernel executes k soft IRQD thread to handle the soft IRQs. So local underscore soft IRQ underscore pending, this is a function which will give us the mask of pending soft IRQs. So it will give us a mask of pending soft IRQs. So in the IRQ handler, I'm first printing the mask, then I'm raising the soft IRQ, then I'm printing the mask, then in the soft IRQ handler, I'm again printing the mask. Very simple code. So when I call raise underscore soft IRQ, then that's particular my underscore soft IRQ bit should be set in the mask. And when I'm executing my handler, that bit should be cleared. So let's verify that. So a lot of interrupts have been generated on a single button, but let's what we do is let's say less. We can see, let me do again, let me clear the kernel and generate again the interrupts. So it's generating a lot. Initially, the value is 0, and when I execute, when this particular raise underscore soft IRQ is being called, it has set the particular bit. So we got 400. When the soft IRQ has started on the processor, it will become 00. And when soft IRQ has been started on the processor, the value will be, the pending will be 00. A lot of interrupts are being generated on a single button click. This is because of debouncing. So when are the pending soft IRQs actually run? So pending soft IRQs, soft IRQ handlers, they are checked and executed at various points in the Linux kernel code. The first one is after the completion of hard IRQ or hard interrupt handlers with IRQ line enabled. We know do underscore IRQ function is the one which is handling the hard IRQs. So do underscore IRQ function, when it finishes handling an IO interrupt, it will invoke the IRQ underscore exit function. And this function is what is checking the calling do underscore soft IRQ. So let's go and check this. IRQ underscore, let's find out IRQ underscore exit. Okay. Let's jump to our, instead of using let's use our Linux x86 code for understanding this. IRQ underscore exit is being called. Now let's call do underscore IRQ. It's mistake with the spelling actually. Should be do underscore capital IRQ. So you have here entering IRQ. which is where the interrupt context starts. And then you have exiting IRQ. Going to exiting IRQ, and you have something known as IRQ exit. And this IRQ exit, what it does is, you can see it is calling, it's checking whether the soft IRQs are pending or not. If they're not pending, that's calling invoking the soft IRQ, and which is actually calling do underscore soft IRQ. If the kernel thread is running, this just written. So this is the first place where the soft IRQs are executed. Soft IRQ handlers are checked and executed, the pending soft IRQ handlers. After the handler is completed, in the IRQ exit function, invoke underscore soft IRQ is being called if there are any pending soft IRQs. Or whenever you call function like local BH enable, bottom half enable, or spin underscore unlock underscore bottom half, which we'll be seeing now. Or whenever this particular thread is run, whenever you call wake up for this particular thread, the pending soft IRQs are executed. So there's a method or a macro which can tell whether you're running a soft IRQ or not. So you have like in underscore hard IRQ, or in underscore IRQ, you have in underscore soft IRQ, which will tell whether you are running a soft IRQ or not. So again, it's a function which is actually verifying whether it is running in soft IRQ or not. I'm calling this function from the soft IRQ handler, as well as I'm calling this function from the IRQ handler. Let's load this into a kernel image. You can see the hard IRQ is interrupt handler is not running in soft IRQ context, whereas the soft IRQ, which is running in soft IRQ context. So in underscore soft IRQ will tell whether it is running in a soft IRQ or not. So disabling and enabling soft IRQs. So we have seen disabling and enabling interrupts, but we also need to know about how to disable and enable soft IRQs. So if a soft IRQ, it is sharing a data with a user context or process context, you have two problems. The process context can be interrupted by a soft IRQ, and the soft IRQ, if it has a critical region, it could be entered from another CPU, which is also executing the soft IRQ. The solution to the first problem is local underscore BH underscore disable. So this will disable the soft IRQ and tasklet processing. Soft IRQ internally, tasklet internally uses soft IRQ. So disable soft IRQ on the local processor, and local underscore BH underscore enable, it enables the soft IRQ on the local processor. And again, these calls can be nested. So if you're calling BH disable multiple times, you have to call the same amount of times local BH enable. Simple example, which is actually disabling the bottom halves and enabling the bottom halves. So this is just a module. So let's copy this and load it for Raspberry Pi. Don't use, let's use Raspberry Pi make file. Let's copy this. This is a module, so we don't end up restarting the image. Not sure what. Let me open one more tab for Raspberry Pi, so we can do a cat on soft IRQs. Watch and cat soft IRQs. There's continuously incremental. Now we have to load our module. The module is loaded. Till and one, you can see one CPU that is not running soft IRQs because we have disabled that on that particular CPU. Now once it has enabled, CPU started running the soft IRQs. Let me again, okay, it's already there. Let me run again. Now this time it is CPU 1 which is not running any soft IRQs. After 10 seconds, start again because we are enabling the soft IRQs. It starts executing again. So local underscore BH enable and local underscore BH disable are used to enable and disable the soft IRQs. So in this example, what we are looking is we are checking what happens when I call spin underscore lock. If I call spin underscore lock, are the interrupts enabled or disabled on the local processor? So to check that, I wrote a simple example where I'm initializing the spin lock. I'm checking here whether interrupts are enabled or disabled by calling our old function. And I'm calling the spin lock. And again, I'm checking whether interrupts are enabled or disabled. What do you think, whether interrupts will be enabled when I call spin underscore lock, or they will be disabled? Let's check. Again, I'm calling spin underscore unlock, and again, I'm verifying whether interrupts are enabled or disabled. I can load this module here itself. So you can see initially interrupts are enabled. When I call spin underscore lock, they are enabled. When I call spin underscore unlock, they are enabled. So spin underscore lock and spin underscore unlock, they do not disable and enable the interrupts. They just lock the particular spin lock. They do not modify anything on the interrupts thing. Then we have one more function, spin underscore lock IRQ save, spin underscore unlock IRQ restore. Let's verify whether these functions actually enable or disable the interrupts. And you can see here, initially interrupts are enabled, but when I call spin underscore lock IRQ save, interrupts are disabled. When I call spin underscore lock IRQ restore, interrupts are enabled. So spin underscore lock IRQ save and spin underscore lock IRQ restore, they modify and they enable and disable the interrupts. If you want to disable and have both spin underscore lock, like if you have multiple CPUs of accessing the same soft IRQ or they're executing the same soft IRQ, then you should need a lock. You can use spin underscore lock BH and spin underscore unlock BH. It performs both spin lock as well as it will disable the bottom half and as well as it will enable the bottom half. So if you have a critical region in the soft IRQ handler, you have to make sure that it is safe from multiple CPU access by using spin underscore lock BH and spin underscore lock unlock BH. So, but spin underscore lock BH, they do not disable the interrupts. They only disable the bottom halves. So we can verify that here. So spin underscore log BH, they do not disable the interrupts. They only disable the bottom halves. So you can use this when you have a critical region in soft IRQs.